We have Jessica Burt from the Smithsonian Institution, as well as our very own Hannah Storch from Pixel Acuity, buzzing about mass digitization, a case study with the National Museum of Natural History's Department of Entomology and Pixel Acuity. So for Jessica Burt, she's the Acting Collections Information Manager for the Department of Entomology at the Smithsonian's Natural Museum of Natural History. She oversees the digital curation of the entomology collection, which includes over 35 million specimens and genetic material. Through the creation and implementation of workflow, she works to increase the collection's digital presence. Hannah Storch is a project manager with Pixel Acuity, specializing in cultural heritage digitization. After obtaining her BA in Classics and History from Grinnell College, Hannah attended Georgetown University, where she received her master's degree in art and museum studies. She has worked in collections and development at a variety of museums and archives, including the National Museum of Women in Arts, National Museum of African Art, the National Museum of Natural History. Her role at Pixel Acuity has enabled her to partner with institutions embracing the opportunities that collections digitization brings to institutions and the communities they serve, along with daily tasks of image production, image processing, staff supervision. Hannah has also created digitization workflows and programs that optimize productivity while emphasizing preservation. Working hands-on with physical collections, Hannah never ceases to be amazed by the ability of cultural heritage institutions to piece together the past one collection at a time. Hannah and Jessica, please turn on your camera and let's load up your presentation. Again, Hannah and Jessica, please wait till the questions towards the end pop up so you can answer them as they appear on your screen. Welcome and thank you.
Thank you.
Thanks, Peter. So, hello, everyone. Thank you so much for joining us today, and welcome to our presentation, Buzzing About Mass Digitization, a case study of the digitization of an entomological collection. My name is Hannah Storch, and as Peter said, I am a project manager with Pixel Acuity, and my co-presenter today is Jessica Burt, who is the Acting Collections Information Manager for the Department of Entomology at the Smithsonian National Museum of Natural History. Today, we will be sharing with you our two-part digitization project, which resulted in the digitization of 2 different entomological collections, shedding some light on natural history collections, which were traditionally thought of as more dark data or inaccessible collections. Throughout this presentation, we will introduce you to the partners involved in this project, as well as the physical and imaging workflows. We will also delve a little bit further into the virtual workflow that captured crucial information about the specimens themselves, and then how this information was linked and shared with researchers and the general public, fulfilling that crucial key museum mission of accessibility. So without further ado, Jessica, take it away.
Thanks so much, Hannah. So the U.S. National Insect Collection is the 2nd largest entomological collection in the world. As noted earlier, we have approximately 35 million specimens. And if we were to digitize this collection in traditional methods where we look at the labels, type in the information directly into our database, it would take us over 67 years to completely digitize the collection. And that's if we had a staff of 20 full-time data entry technicians. So, while natural history collections in general can be complicated to digitize, the nature of entomology collections raises several unique challenges. First of all, we have several different storage types. For example, insects can be preserved wet, where they are stored in jars containing alcohol. They can be slide mounted, or they can be dry, where the insect is penned through the thorax and labels are stacked beneath it. This is what you're seeing in the slide below. Those are examples of our dried collection. And these dried penned insects are really our greatest challenge. They make up the largest portion of our collection. And when these insects are digitized, the labels have to be removed staged, and then put back on the pin in the exact same order that they were taken off. Second, insects are not uniform in size or shape, and these differences can vary very widely even within similar groups. And third, the insect staging and orientation that you need to capture a good image really depends on the group of specimens that you are working with. So this means that you may need to shoot different aspects of the specimen or rearrange your specimen based on groups. And these added camera angles can really complicate digitization. But regardless of all of these challenges, we are committed to digitizing the collection. We want to make it more accessible for scientists and the public. Without digitization, our specimens and their data are only available if you physically possess the specimen. So that means that you would need to get all the required approvals, which usually means lots of paperwork, to come visit the museum and get access to the collection, or you would need to request a loan. And that requires us handling the specimens, packaging them, and shipping them out. Through digitization, we're able to decrease the specimen handling, and we are able to unlock the collection's dark data, and we make that data more accessible for everyone. The need for historical data is one of the reasons that the bumblebees were chosen in our 2015 pilot project. Just before we were asked to finalize our project choice, the White House Pollinator Health Initiative was released. This initiative focused on developing strategies to understand and prevent pollinator loss. They wanted to increase public education, and they also wanted to improve and increase natural habitats. Having a completely digitized collection of a group of pollinators would really increase the knowledge of understanding that chosen group. So when we were contemplating our options, bumblebees became our obvious choice. They're relatively uniform in size, which lended themselves to one-shot imaging, and their charismatic nature made them very attractive for a community transcription project.
So as Jessica's mentioned, the selection of this particular collection was very purposeful, and it lent itself very easily to a mass digitization approach. Natural history collections such as these represent an incomparable resource for information. Knowledge gleaned from these collections has made unequivocal contributions to the study of taxonomy, systemics, biological conservation, climate change, and much more. However, they are often underutilized due to the difficulty of obtaining and analyzing data within and across these collections, and the unique workflows that are required for these projects. Digitization and subsequent dissemination of this type of information solves this problem, but these types of collections present major technical and organizational challenges for digitization. The photographer must capture the specimens and their data quickly enough to effectively achieve digitization of entire collections, but they also have to maintain sufficient quality. In this case, meaning specimen images detailed enough for scientific study and diagnostics, and label images clear enough for transcription and data records. As with many projects of this size and scale, we like to conduct a pilot project before launching into full-scale digitization. So we conducted our first phase of this project in 2015, and then the second phase was conducted over a 6-week period between 2019 and 2020. There were a lot of people involved in these two separate stages, but the key players were the Department of Entomology at the Smithsonian National Museum of Natural History, the broader institution as a whole, and the Smithsonian Digitization Program Office, or DPO. At the time of the pilot in 2015, the National Museum of Natural History had never actually conducted a mass digitization project before. Therefore, the initial goal of this pilot was to test and develop project workflows, but we were actually able to digitize many more specimens than we'd originally anticipated from the bumblebee or bombus collection. We imaged so many of the originally slated collection that by the second phase, we actually were able to include an entire second collection of xylocopa or carpenter bees. By implementing this multi-part project over time, but with the same key players, we were really able to hone our workflows, optimizing efficiency and emphasizing collection care and data management throughout the project. The basic breakdown for this project consisted of 3 separate workflows, which we'll discuss during the presentation today: the physical workflow, the imaging workflow, and the virtual workflow. We will go into a little bit of detail about the physical workflow today, but I would also recommend checking out part 1 of our webinar series, which was hosted by Floyd Shockley, the collections manager for the Department of Entomology. During this presentation, he goes into a little bit more detail about the physical workflow, and this presentation will be made available on the Digital Transitions YouTube page at a later date. For this project, we had 6 handlers comprised of staff from the National Museum of Natural History and Pixel Acuity, who would prepare and stage the specimens and return them to their drawers after imaging. Within the collection storage area, the specimens were housed within unit trays, within drawers, within cabinets. Several of these drawers were then brought to the imaging area at the beginning of the day and returned at the end of the day. Each drawer could contain numerous trays of specimens, with the bees closely packed together and unique identifying labels pinned to each bee. The handlers then had to unpack each of these trays one by one, removing labels from the pins and staging them in the tray next to the specimen. Along with any identifying locality labels, there was also a USNM ENT label, which identified each unique specimen with a distinct number. The handlers would then position the bees in the tray next to the label for the optimal amount of diagnostics. Once the stage was set, in this case literally and figuratively, the trays were lined up on a specifically designed table and fed to the photographer, who would then capture the image of the bee and pass the tray to another set of handlers who were waiting to repin the labels and barcodes and return the bees to their trays. Because of the efficacy of this type of workflow, there really weren't many changes made between the pilot and the production stage for this project. We did calibrate specific tables for this assembly line workflow and imaging space, and that did help the production flow a little bit more smoothly. We also included a project manager from the National Museum of Natural History staff who was able to oversee the day-to-day and also work on the assembly line. Using raw rapid capture combined with mass digitization techniques, we were able to effectively image these specimens throughout the imaging workflow. The term rapid capture refers to the speed and flexibility of the workflow, which allows for digitization of an object to take seconds rather than minutes or hours. Due to the increased speed of actual capture, this actually involves less handling of the specimens, and it's therefore a safer production for this type of mass imaging. One of the main emphases of this project was that the collection information be inextricably linked with the correct specimen, both the image and the file itself. So we were able to shoot one single shot containing both the bee in remarkably minute detail and their accompanying labels. In order to capture these required details for both the specimens and the labels, we captured these images at a minimum of 800 dpi, using a DT RCAM and Phase 1 IQ180. We also included an ISA object level target in each shot to adhere to FADGI standards. Due to the significance for data linking for this particular collection, we also embedded metadata information at the time of capture. So in this case, this included keywords such as Department of Entomology, the creator, Pixel Acuity, and the source, the National Museum of Natural History. But we also were able to include taxonomical information about the specimen itself. This information was gleaned from a taxonomy label that was included with each specimen and then input into the digital file, so that any derivative image that we created would include this information, identifying the types of specimens. The results of this type of project were undeniable and surpassed expectations. Each day, we imaged between 900 and 11,000 specimens. So in round 1, the pilot project in 2015, we imaged 45,000 bees in 40 days. In round 2, we imaged 30,024 bees in 32 days. The end result of this was the digitization of 2 complete collections, the Bombus and the Xylocopa collections, which totaled 75,000 distinct catalog records and specimens. Arguably, some of the greatest improvements between the pilot project and the production phases was the inclusion of automations. The generation and embedding of taxonomy information was one such advancement. So with the assistance of the Smithsonian Digitization Program Office, the SI team was able to create a system that would generate a unique QR code for each taxonomic name identified within the collection. The photographer would then scan the QR code, which automatically generated the correct taxonomy for the specimen, and input it into the requested IPTC metadata field. This meant that each specimen was correctly identified within the system. We also included a USNM ENT label with the taxonomy label, which resulted in a barcode-based naming convention. The traditional approach for this type of naming convention would have involved an operator using a hand scanner, which would read the barcode and then enter the value into our imaging software. During this latter production phase, we were able to use our latest DT pixel flow automation tools to automatically read the value of the barcode from within the image and name and label the digital file accordingly. This improved accuracy, productivity, and resulted in safer specimen handling. This resulted in improved accuracy because the barcode value was not only read, but also instantly verified and validated against known attributes of the barcode. This also improved productivity because the operator didn't have to take any actions relating to the barcode, and they were able to focus more on quality control and QC. Arguably, the most important part is that this was a lot safer for the specimens because the operator could focus 100% of their attention and time to the safe handling of the specimens rather than the inputting of the taxonomic information. Using this same DT PixelFlow software, we were able to automate our file processing and derivative generation for the latter phase of this project. We were able to produce all requested derivatives, which included an 8-bit TIFF, 8-bit JPEG, and full 16-bit RAWs. Along with creating the required assets, we were also able to name and organize them based on the content of the barcode and divide them into subsequent delivery batches with an accompanying MD5 checksum for file validation. These derivatives were then uploaded on a daily basis to the VFCU dashboard for review by the SI team.
As Hannah has just mentioned, we really improved upon the pilot project's workflow by automating as much as possible and streamlining several areas. So this graphic represents the general overflow of the virtual workflow. And basically what happened was images were taken and cropped. At the time of imaging, as Hannah just explained, a taxonomy barcode was used to link the taxonomic name to the image, and the images were all renamed using the automation tool. All of the required metadata was stored in the image or a text file given to informatics. The images and the metadata templates were stored locally, and a hot folder configuration was used to pull everything into the digital asset management for the dams. Once into the dams, the creation of individual catalog records and their linked multimedia records in the CIS was also automated. These 2 newly created records are what internally we refer to as skeletal records because they only contain basic metadata and then the unique USNM number. Once these were in the CIS, records and images were pushed online through the collection search and NMNH searches. This ultimately leads to data aggregators such as GBIF receiving our data through an IPT, which makes the records even more searchable and accessible online. In the pilot, we used access queries to create text files and these data imports that contained basic metadata, the taxonomy, and even the images. These imports could take hours to run, and they were easily interrupted due to network issues or even human error. One of the best things about this project was the quick turnaround time. We go from having an insect that is unknown in the collection to being a basic catalog level record with a published image. Even though at this point we don't have fully transcribed label data, these insects are available online and they are searchable by their taxonomic name or even their unique USNM int number. So at this point, if someone had a time-sensitive project, they could actually download all of the images and they would have the collecting details right in front of them that they would just need to transcribe themselves. Before this was made public, again, you would have to schedule a trip to the museum or ask for a loan, and then you would still have to transcribe this data yourself. So I've mentioned several times about these catalog level records. These are really important to us in entomology and in all of our natural history collections. I just want to give you a back end view of what these look like. So as you can see, there's not a whole lot of unique data. It gives you general information about which collection the specimen belongs to. The bottom pane is empty, where the collector and the locality information would reside, and this is the data that will be appended later on. The linked multimedia record, again, contains its unique name, the creator information, and then a brief description. One piece of this that is missing are the usage rights, and those will be completed after transcription occurs.
So in order to facilitate data retrieval, Pixel Acuity actually assisted with the transcription of these entomology labels. So the entomology labels that accompanied the bee specimens in the captured image were very diverse, since each collector created their own labels independently. So the location of relevant information could vary based on the collection and the collector and the type of labels they were using. Each specimen ended up with at least 2 labels, one being the USNM ENT barcode, and another being the locality label, which contained data including things such as collection dates, collector names, and locality information. Other labels could also include label notes and further information about the specimen and collection, such as type status and collection name and number. My personal favorite was when we received a label that came in a different language, such as Russian or Spanish, because it showed the vast variety of these types of collections. Once we'd input the information into the necessary metadata fields, we submitted our transcription for approval by SI staff.
So once the Pixel Acuity staff member uploaded their transcribed data into DPO's existing framework, which was JIRA, the SI staff were notified that a data set was available for review. We use the International Standards for Data Transcription, ISO 2859, to check the data for accuracy and establish quality control thresholds. This just means that we checked a small subset of the data for true errors. And in this case, a true error was just when data was missing from a transcription field or if it was done incorrectly. Formatting issues or labels that were illegible were not counted as true errors. So using these established guidelines really made our ongoing transcription process efficient. Once the data set was approved, there was still work to be done. So data was then formatted for EMU imports, which included simple parsing, the addition of standard fields, data mapping, and finally georeferencing. So once all this was completed, the data was imported back into the CIS to enhance the original records. And now we have the fully digitized records available online. The transcription process was another area that was quite different between the pilot project and the production workflows. In the pilot, we used the Smithsonian Transcription Center, which was a community-based approach with digital volunteers. And in production, we used Pixel Acuity's paid transcription program. So both accomplish the essential task of data transcription, but just in 2 entirely different ways. So now you can see we're back to the back-end data records where you can see the appended data. On the bottom record, you can now see the collector, locality reference, and then the geo-coordinates are highlighted. Over on the multimedia record, this is where we want to add in the usage rights. Previously, all images that we published contain the right statement of usage rights apply. This means that if someone wanted to use the image in production, that they have to contact the Smithsonian to be granted use. However, in January 2020, which was just when this project was coming to an end, we started the Smithsonian's Open Access Initiative. So under this initiative, we want all images that we possibly can to be in the public domain with the usage right of CC0. So that means that users can enhance and reuse the image without restriction. How do the photos, or how do we decide if the photos get released? Well, any image that contains sensitive information, such as locality information for an endangered species, isn't published at all. Then there are certain locality restrictions that have to be assigned usage rights apply so that we can approve them on a case-by-case basis. But the majority is that we want all of our images that possibly can to be marked as CC0.
Jessica and Hannah, just to give you a quick heads up, we only have a couple minutes remaining.
Okay.
Thank you.
So I'll just quickly go over what some anecdotal evidence that we were able to get, so how these collections were used. So with such a large release of images, they were used to develop machine learning systems. In 2016, the Smithsonian Data Lab developed a pilot program for deep learning that could actually differentiate bumblebee species with a 92 to 97% accuracy. A DPO project officer was also able to use the data labels to automate OCR, to automate transcription for some of the required fields. Both of these results were very surprising to us and really just show some of the things that can be done with this amount of data. Just last month, I was contacted to see if we could confirm the identification of 2 specimens by a fish and wildlife biologist who was trying to create a historical range for collections. They had outliers, and I was able to pull up these images, confirm the identification, so that we could figure out that their original transcribed data was incorrect. This was great news because, you know, they could make better sense of their data and make sure that their model was the best. So as you can see, this requires a lot of collaboration and teamwork. Between the 2 projects, we were able to establish best practices for mass digitization of pen specimens. And we really look forward to expanding on what we've learned in the future for new mass digitization projects.
And we'd just like to say a very quick thank you to everyone who was involved in the different phases of the project, to everyone who was involved in the pilot in 2015, and those who were involved in the second phase between 2019 and 2020. So thank you to everyone, and we look forward to answering your questions.
Thank you.
Hannah, great presentation. Thank you so much for sharing that with us. We should have some questions popping in.
Also, I appreciate the bee puns to everyone who's been throwing those in the chat. Jessica and I had a lot of fun with this one.
I was kind of hoping to hear the fly the bumblebee somehow in the background music while waiting for questions. It'd be very appropriate. I think that's on the SI YouTube video, isn't it?
It is,
Yes.
yeah, the Smithsonian DPO video.
Yeah. Okay, the first question's up. I guess I'll ask it. Is the generated QR code cataloged with the specimen?
So yes, the QR code, the one that you could see in the image, the USNM INT barcode, is cataloged with the specimen. That's its unique identifier and really what we want people to publish on. So that identifier gets sent to GBIF. If any data analysis or genetic analysis is done, that barcode should go to gen bank, we want that to follow the specimen so that we can figure out exactly which specimen was used.
Nice. All right, just wait a sec for another question to pop up, because if not, I have a few. Oh, how many hours per day did the team work on digitizing?
So our
I
average,
assume when they say digitizing, digital imaging or the kind of conversion metadata process. But let's start with, why don't you break it down a little bit, Hannah?
sure.
Dan.
So Peter has responded yes to digital imaging, so I guess we'll start there. So we spent a full day's work, so about 7.5 to 8 hours digitizing. And with that rate, that was over 1,000 individual specimens that were, 100 individual specimens that were imaged per hour. And this saved a large amount of time in terms of capture. So that's, one specimen in less than 1 minute, which is pretty remarkable.
Nice. Okay, here we go. Were you able to use volunteers or students in your assembly line, or were everyone SI or Smithsonian Institution employees?
So the people that were in charge of kind of in the assembly line were paid contractors. They were either under Smithsonian Entomology Department or Pixel Acuity. The pilot project was made up of quite a few volunteers and interns, and also the collection program technicians. And so we really kind of felt that having a dedicated staff of the same core 6 people every day really helped keep this project going smooth.
And as I mentioned, one of the sort of key differences between the pilot project and the second production phase was the inclusion of on-site project managers, both from natural history staff and from Pixel Acuity. So for this project, in this case, I was the project manager from Pixel Acuity and the photographer. And then we also had somebody in the assembly line from natural history who was working as a handler and the project manager from their side. So together we were able to sort of address anything that might arise during the day.
Awesome. Awesome. Okay, were there any objects or specimens that required unique setups, multiple views, specialized lighting? Yeah.
So in this case, we actually just had one view of each specimen, although it did vary. So there was some very careful staging involved. The specimens had to be at the exact same level of with the labels on the stage so that we could get everything in focus. But because we were just taking the one diagnostic view accompanied by the labels, there wasn't too much unique setup required for different shots. We were able to pretty much maintain the same focus level of field, the same lighting setup, and everything.
Excellent. How do you determine the PPI for each capture? Was this done automatically, like so with like the camera system, or through a ruler, or what was the process for that?
So after initial testing, we decided that we need to have at least a minimum of 800 DPI for each capture in order to get all of the required details for both the specimen and the labels in the same one shot. So once we determined that, we actually took a FADGI an ISA device level target at the beginning and middle of each day, and then each individual capture also included an object level target, so certain things could be measured.
Excellent. Excellent. Okay, here's another question from Peter. During the pilot stage, were there some unique learnings that required adjustments for this project, for this bee project?
So we learned so much in the initial pilot project. Hannah touched on this. One of the biggest changes was having these project managers, one from Pixel Acuity and one from SI, that really handled the day-to-day oversight. Hester Dingle was our SI handler. That was our kind of our on-site project manager. And any question that the others had would be relayed to Hester. If she couldn't resolve it on her own, myself or Floyd Shockley would get a text, and we would fix any problems kind of on the fly. For the physical handling, Hannah mentioned this, but we had table ledges for the pilot. When they would disassemble the labels, they would slide the specimens down the table, and a couple almost fell off. So we used this weird makeshift ledge. So in the production, we made sure that we had custom table ledges so that the specimens were very safe. There was a lot of automation for the virtual workflow, and also our transcription was different. So that wasn't necessarily an improvement, it was just different. But yeah, we were constantly making adjustments to how we laid out the project.
Nice. Well, let's see if we have a couple more questions come in. If not, I have one. So I'll just throw it out there. Is this part of a larger effort to digitize and catalog the animal kingdoms that are stored in various repositories throughout the world? Or you are kind of like, not saying doing your own thing, because obviously you have to coordinate with peer institutions, but are you kind of leading this charge, or how does that all work at the moment?
So all of the natural history collections, there's just a big push to get our data out there. When you walk into a natural history museum, you're only seeing like 2% of our collections. And a lot of times it's not, at this point, I think that there's only 150 insects that are actually on display. So you're just, you're not seeing any of our entomology specimens. Mm-hmm. The real work's kind of done behind the scenes. So there's different projects that are going on right now. There's a terrestrial parasite tracker where we're trying to get host parasite interactions published. There's a big bee initiative where they're trying to get pollinators published, which this fits nicely into. So yeah, there's just a big push throughout museum communities and especially entomology to digitize these and make them just more accessible. Because they're not doing anybody any good just stuck in a drawer. We want people to know that they exist, and we want them to use the data.
Gotcha. So that means there's like a giant shared database, or?
Right. So we use a database called EMU, and then that pushes its data out to other aggregate sites. So the main one that we talk about is GBIF. So they collect data from Symbiosis, Scan, all of these other museums, and it's all there. So if you were to go to GBIF and search Bumbus, you would get all of our digitized specimens. You would get them from the Field Museum. You would get them from the Milwaukee Museum. Everybody's are right there.